Hello viewers, this is Wargada now taking you through the story of A-Level Physics Paper 1, and this video I'm going to go through the marking guide of Senior 5 beginning of Term 3 exam for Paper 1. So this I had earlier sent the question paper, so now you're going to go through the marking guide so that you can mark yourself and check your progress. So these were the table, the constants which could be used where necessary. So we shall start with question 1, and part A, Roman 1 says, state the law of conservation of linear momentum. So let's start with that. So the law of conservation of linear momentum states that when two bodies collide, total momentum before collision is equal to total momentum after collision, provided there is no external force applied. So this last bit, most students forget it, but it's very, very vital. So that was Roman 1. Now we shall go to Roman 2. So Roman 2 says, a body of mass m1 moving with a velocity u1 collides with a stationary body of mass m2. The bodies move with velocities v1 and v2 respectively after collision. If the collision is perfectly elastic, you know that word, perfectly elastic, show that u1 is equal to m1 plus m2 over m1 minus m2, everything multiplied by v1. So perfectly elastic means both momentum and kinetic energy are conserved. So you start with conservation of momentum. I shall say that m1, remember the initial velocity for the second particle was 0. That's why here you only see the momentum for m1. For m1, yeah. So m1 u1 is equal to m1 v1 plus m2 v2. So when I rearrange and collect like terms for m1, this will go this side to become m1 in brackets u1 minus v1, because this has gone this side, it has become a minus, is equal to m2 v2. So that is equation 1. Next is conservation of kinetic energy. So conservation of kinetic energy, we shall say a half m1 u1 squared is equal to a half m1 v1 squared plus a half m2 v2 squared. These are half can cancel, so when it cancels and I make m1 the subject, so bring this one this side, this time this side, you'll come up with m1 in brackets u1 squared minus v1 squared equal to m2 v2 squared. Then next you realize that this is the difference of two squares, so we'll come and expand it to become u1 minus v1 in brackets multiplied by u1 plus v1 in brackets. So that is equation 1, and that is equation 2, and we also have equation 1. So next is to divide. So when I divide equation 2 by equation 1, I'll come up with that expression. So this is here and this is there. Then this is here and this is there. So after that you realize that this m1 can cancel, this one can also cancel, and this m2 can also cancel. Then this v2 goes with one of the v2 in the numerator. So what happens, you'll come up with v2 being equal to u1 plus v1. So that is equation 3. So before we go to the next slide, let's see marks for this slide. So those are the marks. 1 mark for the Newton's law, for the law of conservation of linear momentum, half a mark for equation 1, half a mark for equation 2, half a mark for dividing the two equations, and half a mark for the outcome after division. So substituting equation 3 into equation 1, we shall come up with that. So here there was V2, now we have put the expression for V2 which we got in equation 3, which was U1 plus V1. When I open brackets, I'll come up with that. And when I rearrange to bring U1s this on one side and V1s on the other side, this U1 will go this side to become M1U1 minus M2U2. Then this one will also come this side to become M1V1 plus M2V1. So this step you realize that U1 is common in both terms of the left hand side, and here V1 is common in both terms of the right hand side. So what we are going to do, for the right hand side you are going to factorize out U1, and for the left hand side we are going to factorize out V1 to come up with that. The next is to get the required expression. So make U1 the subject, this one goes this side to become M1 plus M2 over M1 minus M2, everything multiplied by V1. So basically that is what they wanted. So now we shall go to part B. So part B says two particles of mass 2.5 kilograms and 3.0 kilograms moving at velocities of 2.0 meters per second and 1.2 meters per second respectively in the direction at right angles. Know this word, right angles, to each other, collide in a perfectly inelastic collision. Know that word, perfectly inelastic collision. Calculate the magnitude and direction of the final velocity of the particles. So yeah, first of all, we shall interpret what is given. M1 is that 2.5 kilograms and M2 is 3. Corresponding velocity is U1 is 2 and U2 is 1.2. So the first thing to do is to make a simple sketch of the interpretation. So that was M1, which is the 2.5 kilograms, but they said it is at right angles with this M2 of 3 kilograms, so we shall put M2 there because they are moving towards each other. Then after collision, that means that the resultant motion will be there, because they told us it is perfectly inelastic, meaning they stick together and they move together. So by conservation of linear momentum, here what we do, we consider vertical component alone and also horizontal component alone. So for the vertical component, we shall come up with this. So M2 vertical component means that this one is not there initially, it is only this one which is entirely vertical. That's why you see here M2U2. Then after collision, both are, you resolve this one vertically, because the angle is lying on the horizontal, it implies that it's the horizontal which will have cos and the vertical will have sine. Therefore that is why you see here M1 plus M2, which is the resultant mass, multiplied by V sine theta, which is the component of velocity along the vertical. What about along the horizontal? So along the horizontal, this one is entirely vertical, so it cancels out. You remain with M1U1, which is there. Then here you resolve this one, you resolve the velocity to the horizontal. When I resolve the velocity to the horizontal, it will have cos. So here it becomes M1 M plus M2, which is the total mass, multiplied by V cos theta, which is the horizontal component of the resultant velocity. So before we go to the next slide, let's see marks for this slide. So I have a mark for substituting 3 into 1, half a mark for expanding, and full mark for the required expression. Then half a mark for sketching the given information, half a mark for the conservation of linear momentum for vertical component, and also half a mark for conservation of linear momentum for horizontal component. So these two equations, we can divide them. When I divide this equation 1 by equation 2, I'll come up with, this side it will be m2u2 over m1u1. By this side, the m's will cancel and the v will cancel, so remain with sine theta over cos theta, which is the same as tan theta. So here we will come and say that tan theta is equal to m2u2 over m1u1 as we saw before. Then I will substitute for m2u2 m1u1. So when I use a calculator here, it will give me 0.72. Therefore, arctan of 0.72 gives me the value of theta, which is 35.75 degrees. Therefore, from equation 1, we shall come and say that V will be equal to, so when I make V the subject, I'll come up with this expression. Therefore, substitute for M2, U2, M1, M2, and theta. So when I use the calculator here, I'll come up with 1.12 meters per second. Therefore, I'll come and conclude that the final velocity of the particle is 1.12 meters per second in the direction 35.75 degrees to the initial direction of the 2.5 kilogram mass. So that was part B. Now we shall go to part C. So part C, Roman 1 says, state the work energy theorem. So the work energy relation states that the work done by a resultant force, note this word, resultant force, on a body is always equal to the change in kinetic energy of the body. So that is the work energy relation or the work energy theorem. So half a mark will be this substitution, half a mark for getting the angle, half a mark for the substitution, full mark for this magnitude and the unit. So the unit has to be correct. Half a mark for the magnitude, half a mark for the unit. Then this full mark for stating the work energy relation correctly. So now we shall go to Roman 2. So C Roman 2 says, use Newton's equations of motion to derive the relation. So they wanted to derive this relation of work energy relation, which says that work done is equal to change in kinetic energy. So we shall start by defining some of the symbols we are going to use. So M will be for the mass, so consider a body of mass M, meaning that M will denote mass, moving with a velocity U, so U will denote initial velocity. If a force F, so F will denote force, acts on the body at a time T, so T will denote time, and its velocity changes to V, so V will denote the final velocity, in a distance S, so S will denote distance or displacement. So this introduction is very vital because you have to define the symbols. Every symbol you're going to use in the derivation has to be well defined. The next we shall start that F equal to ma, because this is the Newton's second law. Then also V squared is equal to U squared plus 2as, which is third equation of motion. So in this case, when I make as the subject, I'll come up with as being equal to V squared minus U squared over 2. Then I'll come and remember that work done is equal to force times distance. So force times distance, this force is ma and the distance is s. Then then after that I remember that AS was this, so I'll come and substitute it here, and this M remains, so it is there. After that I realized that this one is common, so it can come out to become a half M in brackets V squared minus U squared. Then when I open the brackets, I'll come up with a half M V squared minus a half M U squared, which is change in kinetic energy. So I've derived that work done is equal to change in kinetic energy, and that's what they wanted. So now we shall go to Roman 3. So Roman 3 says, explain why a high jumper flexes his knees on landing on a hard surface. So shall come and say that by flexing his knees while landing on a hard surface, the time taken, know that word time taken, by a long jumper to come to rest is increased. Know that word increased. But momentum change, or change in momentum, remains constant. Because the velocities have remained constant, the velocity before he lands and the velocity after landing have remained constant, so momentum has remained constant. This reduces the rate, know this word rate of change of momentum, thereby increasing the reducing the impulsive force. Remember, rate of change in momentum is proportional to force. Therefore, when the rate of change in momentum reduces, also the force reduces. So reduces the impulsive force exerted on the long jumper in accordance with Newton's third law of motion. Less damage is thus felt in the joints of the long jumper. Remember, Newton's third law of motion says that for every action there is an equal and opposite reaction. So when he lands with a reduced change in momentum, it implies that the reaction of the ground to the knees or to the feet of the long jumper will also reduce. So those are the marks for this slide. So half for stating this equation, F equal to ma, half for stating this third equation, half for stating the formula for work done, half mark for substituting, and half full mark for the required expression. Then for Roman 3, half a mark for stating that the time increases. Then half a mark for stating that the change in momentum remains constant. Full mark for stating that the rate of change of momentum reduces. Then a full mark for stating that the impulsive force reduces. So now shall go to part D. So part D, Roman 1 says, what is meant by dimension of a physical quantity? So we shall say that the dimension of a physical quantity is the way that given quantity is related to the basic, you can use the word basic or fundamental quantities, and you also state them that these quantities are three, and there is mass, length, and time. So that was Roman 1. Now we shall go to Roman 2. Roman 2 says, the maximum power, capital P, developed by the wind turbine is related to the blade radius R, driving wind speed V, and density of air sigma. Derive the expression for maximum power using the method of dimensions. So this P is related to R, which is radius, and it's the same as length. V, which is speed, and sigma, which is density. Therefore, shall come and say P will be equal to R raised to the power X, which we don't know, V raised to the power Y, which we don't know, and sigma raised to the power Z, which we don't know. And we have to get these values of X, Y, and Z. So the next is to study the dimensions for each. So dimension for P is that, dimension for R is that, dimension for V is that, and dimension for sigma is that. Now here what you should realize is that it is this symbol which is in box bracket to mean that I'm getting its dimension, but the dimension is not in a box bracket. So if by mistake you put this dimension, this one, in a box bracket, it will not be okay, because it will imply that you are looking for the dimension of this, which is already the dimension of P which they want. So always be keen when you're putting the box brackets. Then R is length, which is that, velocity is that, meters per second, which is meters is length, and seconds is time. Then density is that, kilogram per meter cubed. So kilogram is mass, which is m, and meter cubed is length, which is L to power negative 3. So next is to substitute in this. So to substitute in those dimensions using that relation. So when I substitute, P will be there, R is there, V is there, sigma is there. The next is to remember the laws of indices. Same base, you add the powers. So here there is this L, there is this L, and there is this L. So this L has X, this L has Y, and this L has negative 3Z. So that is why you see here X plus Y minus 3Z. For M it is only 1, which has a power Z, and for T is only 1, which has a power negative Y. So after that I'll start equating. So when I start with M, I'll realize that this M there is power is 1, and this M the power is Z. Therefore 1 is equal to Z, implying that Z is equal to 1. The next is for T. For T, this side it is the power is negative 3, and this side the power is negative Y. Therefore negative 3 is equal to negative Y, implying that Y is equal to 3. Then for L, this side it is 2, and this side it is X plus Y minus 3Z. So I'll come and say 2 is equal to X plus Y minus 3Z. But the good thing, I know the value of Y and the value of Z. So I'll come and substitute, and I remain with only one unknown, which is X. Therefore when I make X the subject, it will be 2. Now that I've got X, Y, and Z, I'll come and substitute them here to get the required relation, which is that. So basically that is what they wanted. Now let's see the marks for this slide. So 1 mark for the definition of dimension, half a mark for substituting all the dimensions correctly, half a mark for expanding the powers and collecting like terms on each side, then half a mark for getting the value of Z, half a mark for the value of Y, half a mark for the value of X, half a mark for stating the correct relation. So that was question 1. Now we shall go to question 2. Part A, Roman 1 says, what is meant by moment of a force? So you have said that moment of a force is the product of the force and the perpendicular distance of its line of action from the pivot. As simple as that. So next we shall go to Roman 2. Roman 2 says, state the conditions required for mechanical equilibrium to be attained. So the first condition says that the algebraic sum of all the forces on a rigid body must be 0. Then second condition is that the algebraic sum of the moments of all the forces about any arbitrary point must be 0. So those are the two conditions. So have full mark for the definition of moment of a force, 1 mark for the first condition, 1 mark for the second condition. So now we shall go to part B. So part B, Roman 1 says, a uniform ladder of mass 40 kilograms and length 5 meters rests with its upper end against a smooth vertical wall and with its lower end at 3 meters from the wall on a rough ground. Find the magnitude and direction of the force exerted at the bottom of the ladder. So here the first thing to do is to make a sketch of the given information. So we have a vertical wall and a horizontal ground. Then next we have a ladder resting on both. So we don't know the angle, but the good thing we know the lengths. So the first force will be the weight of the ladder, which was 40 kilograms, so the weight will be 40 G. Then we know that AB is 5 because we are told that the ladder is 5 meters. Then AD is 2.5 because this is a uniform ladder, meaning that the center of gravity is at the midpoint. So it divides this length into 2. Now SC is the distance of the foot of the ladder from the vertical wall, and it was given as 3 meters in the question. So that you realize that when they tell you that the ground is rough, it means that there is both horizontal and vertical components. So in other words, there's normal reaction and the frictional force. So normal reaction at A is R1. There will also be frictional force, which is F1. Now it's in this direction because if this ladder was to slide, it would slide going in this direction. But remember, friction opposes motion, so it has to act in this direction. For the vertical wall, they told us it is smooth. So each time they say that the surface is smooth, just know that it's only normal reaction which exists. So at this point, only normal reaction will exist. So now we have to get this angle. So for triangle ABC, we shall realize that cos is equal to 3 over 5 because cos is adjacent over hypotenuse. So the adjacent is SC, which is 3, hypotenuse is 5, which is AB, which is 5. But when it comes to sine, it is opposite over hypotenuse. So opposite by Pythagoras theory, it will be 5 squared minus 3 squared, everything under root. Then the hypotenuse is 5, which is here. So this one gives me 4 over 5, which is 0.8. So I've got cos and sine because they are the ones I'll use in getting moments. But even if you get the angle from here and use the angle, it is also okay. So taking moments about A, we are going to take moments about A. Now when we take moments about A, we shall remember that all forces whose line of action passes through the pivot have 0 moments. So this force has 0 moments, so we shall cancel it out. And this force has 0 moments, so we shall cancel it out. So we remain with this and this. So we shall start with R2. If you stand here, this is the pivot, this R2 will have a clockwise moment, and this 40G will have an anti-clockwise moment. So the formula for taking moments is FD sine theta, where F is the force, D is the distance between the pivot and the point where the force starts from, and theta is the angle between the force and the rod or the ladder. Therefore, when I come here for this part, F force is R2 and D is 5, because from here, from this pivot up this point where the force starts from is 5. That's why they put 5 here. Then sine theta, because theta is the angle between this force and the ladder. So that is for R2. What about for 40G? 40, this side still we use FD sine theta. F is 40G, which is there. Then D is 2.5, because the distance from the pivot to the point where the force starts from, which is AD, and AD we got it as 2.5. Then sine theta, now the angle between the two, this force and this rod or the ladder, is 90 minus theta. That is why you put 90 minus theta there. Then after that, you shall remember some trig identity, that sine 90 minus theta is equal to cos theta. Then G is 9.81 in physics. So now that I've got that, I remember that cos theta is 0.6 and sin theta is 0.8. So I'll come and substitute. From at this point, you realize that we have only one unknown, which is R2. So I'll simplify, and after simplifying, I'll make R2 the subject. So before I go to the next slide, let's see marks for this slide. So this full mark is given for all forces correct, and these forces must be drawn using a ruler. Then half a mark for taking moments on the left hand side, or taking this clockwise moment, and half a mark for taking the anti-clockwise moment. Then half a mark for making R2 the subject. So after getting R2, I'm going to come and resolve horizontally. So when I resolve horizontally, it implies that this force to the left is equal to, this force to the right is equal to this force to the left. Therefore, R2 is equal to F1. So I'll come here and say that resolving horizontally, F1 is equal to R2, but I already know R2, therefore F1 is equal to 196.2 newtons. What about resolving vertically? When I resolve vertically, upward force is equal to downward force, therefore R1 will be equal to 40G. Therefore I'll come and say that vertically R1 is equal to 40G, but the good thing I know that G is 9.81, so I'll come and substitute for G and use the calculator to come up with 392.4 newtons as R1. So now that I've got R1 and R2, I'll come and draw my right angled triangle and put the horizontal component, then also the vertical component. Now how is this diagram drawn? So you start with the horizontal component, but horizontally, this force, if you look at this F1 in the diagram, you realize that F1 is going to the left and this R1 is going upwards. Therefore, when you're drawing your right angle triangle, you start with the horizontal, which goes to the left, and where this horizontal force stops, that is where this vertical force starts from, and it was upwards, so it has to go upwards. Then you use a ruler to join from start to end, and that will denote the resultant force which they want, and that will be RB. But when they remember, force is a vector quantity, so you also have to get the direction. Therefore, now I have with this angle, I have this opposite and this adjacent. Therefore, I can use tan to get the direction. So before I get tan, let me first get this magnitude. So magnitude, I'll use Pythagoras theory, which will be square root of 196.2 squared plus 392.4 squared to give me 438.7165 newtons. Then when I use SOHCAHTOA, I realize that tan beta is equal to opposite over adjacent, which will give me beta as 63.43. Therefore, I'll come and conclude that the force exerted at the bottom of the ladder is 438.7165 newtons in the direction 63.43 to the horizontal ground. So now we shall go to Roman 2. So Roman 2 says, state 2 instances where increasing friction is useful. So the first one is in sharpening of blades. Then 2 is in walking. 3 is during braking of a vehicle. And 4th is during lighting of a matchbox. So any of those is okay. So in this slide, half a mark was for resolving horizontally and getting this force, half a mark for resolving vertically and getting this force, half a mark for substituting in Pythagoras theory, and half a mark for output, half a mark for the angle. Then here, half a mark for any 2. So you only state any 2. So you can say these ones, or you say this and this, or any two you want, you can state them. So now shall go to part C. So part C, Roman 1 says, state the laws of dynamic friction. So there are 3 laws. We shall start with the first law. First law states that friction of force acts parallel to the surfaces in contact in a direction so as to oppose their relative motion. So that was the first law. Then the second law states that friction of force depends on the nature of the surfaces in contact, but independent on their area of contact, provided normal reaction remains constant. So that was the second law. Now we shall go to the third law. Third law states that when the surfaces are in contact, when the surfaces in contact are in relative motion, remember we are dealing with dynamic friction, meaning there is relative motion. That is why we are concentrating on the relative motion. So when the surfaces in contact are in relative motion, dynamic friction is directly proportional to normal reaction and independent on their relative velocity. So that was Roman 1. Now we shall go to Roman 2. So Roman 2 says, define coefficient of dynamic friction. So we shall come here and say that the coefficient of dynamic friction is the ratio of dynamic friction of force to normal reaction for 2 surfaces in contact. So the marks for 1 mark for the first law, 1 mark for the second law, 1 mark for the third law, and 1 mark for this definition. So now shall go to part D. So part D says a block of mass 2 kilograms placed on a horizontal table is pulled by a mass m using an inextensible string that passes over a frictionless pulley as shown below. So in this case they have helped us by drawing the sketch, but you must be able to read the question and draw the sketch by yourself. So in this case they helped us and made this question a little simpler. So the block moves with a constant velocity when m is 600 grams. Note this word, constant velocity. Constant velocity means acceleration is 0. Calculate the coefficient of friction between the block and the table. So the first thing to do is to redraw the sketch which was given. After that we shall show the forces. So that's what was given. Next is show the forces. We shall start with the weight. So this one, 600 grams is 0.6 kilograms. So this G does not mean grams, it means acceleration due to gravity. So this is the mass, which is 0.6 kilograms multiplied by the acceleration due to gravity to come up with the weight. Now because this one is facing downwards, here tension will face upwards, and because this one is facing upwards, here tension will face downwards. And because this is here, this will go to the left, and because it's going to the left, this will go to the right. So they have to be in opposite directions. Then for this mass, we shall put the weight as 2g. Then because this one is facing downwards, the normal reaction will face upwards, which will be capital R. Then from there, I remember that this one is moving in this direction, downwards. But the acceleration is 0 because the velocity is constant. And this acceleration is the same acceleration for this other particle. And it is also 0. Now because the direction is going this direction, and this surface is rough, it means that friction will oppose motion by going in that direction. So you come and put friction force as mu r. So next is to resolve. So when I use F equal to mf for the 0.6 kilogram mass, I realize the resultant force is this minus this. Why? Because this acceleration is pointing downwards, therefore this one is bigger than this. So it will be 0.6 g minus t equal to ma, where m is 0.6 and a is 0. Therefore come and substitute for g, and this side is 0, so t is the only unknown. When I make it the subject, it will be 5.886 newtons. Then still use F equal to mf for the 2 kilogram mass. Acceleration is pointing in that direction, meaning that the resultant force will be T minus mu r equal to ma, where m is 2. So I'll come and substitute T minus mu r is equal to 2 times 0. The good thing, I've got T, and I know that R is equal to mg, which is 2 times 9.81. So I remain with mu as the only unknown. Therefore, I will simplify and make mu the subject, and mu will be 0.3. So that was part D. Now we shall go to part E. So part E Roman 1 says, what is meant by time of flight? So time of flight is the time taken by a particle to return to the same, know that word, same horizontal level as the point of projection. So now let's see the marks for this slide. So 1 mark for this first diagram drawn using a ruler, 1 mark for using F equal to MA for 0.6 gram mass, and half a mark and half a mark for the output. Half a mark for using F equal to MA for the 2 kilogram mass, and half a mark for the output. Then full mark for the definition of time of flight. So now shall go to Roman 2. So Roman 2 says that show that the equation of trajectory is parabolic in nature. So first of all, we shall state the equation of trajectory. Then after stating it, we shall come and say that theta, G and U are constant because there is only one angle of projection, and there is also one initial velocity. So these are constants, and this one is already known that it's a constant. Now since they are constants, this equation will reduce to y equal to ax plus bx squared, where a is tan theta and b is g in bracket. So b is the whole of this, remove this x squared which is here, so the remaining part is g multiplied by brackets of 1 plus tan squared theta, everything divided by 2u squared, which is that. So when I replace the whole of this with b and the whole of this with a, I'll come up with this as the equation of trajectory. Now they say that they want you to show that it is parabolic in nature. So in math 1, with time you'll cover what a topic called conic sections, and that conic sections has special curves. 1 is a parabola, 2 is a hyperbola, and 3 is an ellipse. Now a parabolic comes from the word parabola. So a parabola, in simple terms, since we have not yet covered it, we shall say that all quadratic equations reduce to a parabola if you complete squares. Therefore, this is a quadratic equation, so the aim is to complete squares for this equation, and we see how it reduces to a parabola. So to complete squares, the coefficient of x squared must be positive 1. So what does that mean? It means that I'll come and factorize out negative b, which was the coefficient of x squared, because for it to complete squares, this coefficient of x squared must be positive 1. As you can see it here, it is now positive 1. Then next is to use the formula for completing squares. So how is the formula? The formula says get this coefficient of x and divide by 2. That is why you see here a over 2b. So it becomes x minus a over 2b, in brackets you square the whole part, the whole of the expression. Then minus, now minus, you will say that new term, which is a over 2b squared. That is why you see here a over 2b squared, and here it is minus. So this is the formula for completing squares. It will be taught more in math paper 1. So after that, we shall now try to open this square bracket to come up with that. Then we rearrange, make this one the subject. So that means that this has to go this side and this one also has to go this side. So let me start by putting this one this side to come up with this expression y minus a squared over 4b equal to negative b, in brackets this expression. But my aim is to make this one the subject, so I'll bring this one also this side to come up with that. Now I've completed squares, and I'll come and conclude that this equation is in the form x squared equal to ky, where k is a constant, hence a parabola, or it's a parabolic in nature. So I think we realize that this capital X will denote the whole of this bracket, but there's a square, that's why there's a square here. Then the whole of this negative 1 over b will denote this k, and the whole of this bracket will denote capital Y, and that is the form of a parabola. So now let's see marks for this slide. So half a mark for stating the equation of trajectory, half a mark for reducing it by substituting it with constants a and b, then half a mark for completing squares, half a mark for expressing in the required expression of a parabola, then half a mark for concluding. So that was question 2. Now we shall go to question 3. So question 3, part A says define the following: Roman 1 thermometric property and Roman 2 triple point of water. So for a Roman 1, we shall come and say that the thermometric property is a physical property of a substance whose value varies linearly, so you can use the word linearly or uniformly, and continuously with temperature. So both these words are needed. Most students write only this one of linearly and forget this word continuously. That will not be a complete definition. So it should be that it varies linearly and continuously with temperature. Then Roman 2, they want a triple point of water. So we shall come and say that triple point of water is the unique temperature where all the three states of water, that is pure water, pure melting ice, pure saturated vapor, coexist. So this word is very vital. Coexist in equilibrium. So 1 mark for this definition, 1 mark for that definition. So now we shall go to part B. So part B, Roman 1 says, with the aid of a labeled diagram, describe the operation of a constant volume gas thermometer. So such a description is easily done with a diagram. So what we are going to do, let's first draw our diagram of a constant volume gas thermometer. So next is to label some of the parts. So we shall start with that part, which is a gas bulb containing a gas such as helium. Then next we shall label this as the dead space. Then next we shall label this as the movable tube open to the atmosphere. So this is the atmospheric pressure. Then next we shall label this as the mercury, and this as the flexible rubber tubing. So here we shall award marks for any 4 correct labeling. So any 4 correct labeling with the correct diagram, you'll get yourself the 2 marks. So now we shall start our description and say that a constant volume gas thermometer is as shown above and is used to measure temperature. Then next we have said that the bulb containing the gas is immersed in an enclosure whose temperature is to be measured. So after that, time will be allowed for the gas to acquire a temperature of the enclosure. Then when that is done, the flexible tube is adjusted to bring the mercury level to the reference mark R. Then the difference in the mercury levels, which is H, I think you saw it on the diagram, is measured and recorded. The gas pressure P theta, which is given by H plus or minus small h. So this one plus or minus means that it depends on the value of H. So H can be above the, for example, when you go to this diagram, if you go to this diagram, this mercury level may be above this reference mark or below. So in this case it is above, so it will be plus, but if it is below it will be minus. So that explains why here we put plus or minus to cater for both cases. So that is P theta. Then the bulb is then immersed in ice water mixture and the pressure P naught is obtained, still using this formula. So before we go to the next slide, let's see marks for this slide. So half a mark for this, putting the bulb in an enclosure, half a mark for allowing it to acquire the temperature of the enclosure, half a mark for measuring the mercury level difference, half a mark for this getting the gas pressure at that unknown temperature, and half a mark for the gas pressure at ice water mixture. So after removing it in the ice water mixture, next we shall immerse the bulb in steam, and the gas pressure P100 is also obtained. So now we have P theta, we have P naught or P at ice water mixture, and we also have P100. Therefore we shall use those parameters to come up with the unknown temperature using the formula that theta is equal to P theta minus P naught over P100 minus P naught, everything multiplied by 100, and to be degrees Celsius. So that was Roman 1. Now we shall go to Roman 2. So Roman 2 says, list 3 corrections necessary in the constant volume gas thermometer. So the first one is that the bulb must be made of hard glass to limit thermal expansion. Then the second one is that the dead space should be made narrow. And lastly, the third one is that the manometer tube should be narrowed. So now we shall go to part C. So part C, Roman 1 says, state Newton's law of cooling. So you come and say that Newton's law of cooling states that the rate of heat loss by a body is directly proportional to its excess temperature over that of the surrounding under conditions of forced convections of air. So this word is needed. Forced convections of air, or you can say drought. So let's see marks for this slide. So half a mark for measuring P100 and full mark for stating the formula to be used to get the unknown temperature. Then one mark for each correction, and here 1 mark for for stating the law. So now shall go to Roman 2. So Roman 2 says, explain why a small body cools faster than a large one of the same material. So you have said that the rate at which a body loses heat is directly proportional to its surface area to volume ratio. What does that mean? It means that a small body has a larger surface area to volume ratio than a larger one, and hence cools faster than a larger one of the same material. Know this word, same material. So that was Roman 2. Now we shall go to part D. So part D says, a heating coil is immersed in 100 grams of paraffin contained in a copper calorimeter of mass 100 grams. A current of 2.5 ampere flowing through the coil causes a temperature rise of 10 degrees Celsius. If the 10 degrees Celsius in the paraffin in 100 seconds. Calculate Roman 1 the total heat absorbed by the system. So we are given that specific heat capacity of paraffin is 2000 and that of copper is 400. So here I shall come and say that total heat absorbed is equal to the heat gained by paraffin and calorimeter. Therefore, the one gained by paraffin will be this, and the one by calorimeter will be that. So you shall come and substitute. For paraffin, M is 80 grams, so you change to kilograms. C is the specific heat capacity, which was 2000, and change in temperature was 10 degrees Celsius. For the calorimeter, mass was 100 grams, so you change to kilograms. C is the specific heat capacity, which is 400. Change in temperature was 10. So when I use the calculator, I'll come up with the total heat absorbed as 4000 joules. So for this slide, 1 mark for stating that, 1 mark for the word larger surface area, and 1 mark for cooling faster. Then 1 mark for stating the formula for heat gained by both paraffin and calorimeter, 1 mark for substituting, and 1 mark for the final answer. So now we shall go to Roman 2. Roman 2 says, calculate the reading of voltmeter connected across the coil. So at thermal equilibrium, it means that heat lost by the heater or the coil is equal to total heat absorbed. Therefore, heat lost by the heater is IVT, and total heat absorbed, we already saw it as 4000. So I'll come and substitute for current and for time, and I don't know V. So V is the only unknown. Next is to make it the subject, and to be 16 volts. So 1 mark for stating the formula, 1 mark for substituting, 1 mark for the final answer. So that was question 3. Now we shall go to question 4. Question 4 part A says define the following: Roman 1 isothermal change, and Roman 2 critical temperature. So Roman 1, we shall come and say that isothermal change is a change in pressure and volume of a fixed mass of a gas at constant temperature. So isothermal means temperature is constant. Then when it comes to critical temperature, we shall come and say that critical temperature is the maximum temperature required to liquefy a gas. Alternatively, you can also say that critical temperature is the temperature above which a gas can't be liquefied no matter how great the pressure may be. So it is the same definition, it's only the English which is being altered, but all are correct. So 1 mark for this definition, 1 mark for this definition, so you only give one definition here. So now we shall go to part B. So part B says the equation of state for 1 mole of a real gas of volume V and pressure P at temperature T is given by this expression, where A and B are constants. Explain the significance of the terms A over V squared and B. So shall come here and say that the intermolecular forces of attraction are not negligible, and this leads to a pressure defect that accounts for the term A over V squared. Then after that we shall say that the volume of the molecules may not be negligible compared to the volume of the container occupied by the gas. Note this word compared to. So it has to be stated. Therefore, the cofactor B accounts for the finite volume of the molecules themselves. So that was part B. Now we shall go to part C. So part C, Roman 1 says, state the kinetic theory of matter. So we are coming to say that kinetic theory of matter states that matter consists of tiny particles which possess energy and are therefore always in constant, know this word constant, vibration in solids and continuous random motion in liquids and gases. So because they said matter, you have to state what happens in solids, what happens in liquids, and what happens in gases. So for solids it's constant vibration, but for liquids and gases it is continuous random motion. So half a mark for stating that intermolecular forces are not negligible, and half a mark for this pressure defect which accounts for this expression. Half a mark for stating that the volume of molecules is not negligible compared to the volume of the container, and half a mark for stating that factor B accounts for the finite volume of the molecules. Then half a full mark for the definition. So now we shall go to C Roman 2. So C Roman 2 says, describe briefly an experiment to demonstrate the kinetic theory of matter. So such a question is also easily done by making a sketch. So we shall come here and make a sketch. So next is to do the labeling. So the first one will be that one, which will be glass rods or converging lens. Then that one is the glass slide. This is a microscope, and these are smoke particles which are visible, and these are air molecules which are invisible. Then this is the glass cell. So here, any two correct labeling with the correct setup, you get to save that one mark. So now we shall come and say that the setup is as shown above. Then from there we shall come and say that the smoke is confined in a smoke cell and viewed through a high power microscope. So with strong light from the side of the cell, the particles of smoke are seen as bright specks in continuous random motion and never stopping, requiring no supply of energy from outside. So something must be in constant collision with the smoke particles, and these are the invisible air molecules. So thus we shall conclude that tiny particles of matter are in continuous random motion. So half a mark for confining smoke in a smoke cell, half a mark for stating that these smoke particles are in continuous random motion, half a mark for stating that there should be invisible air molecules which are in constant collision with the smoke particles, and half a mark for concluding. So now we shall go to part C, Roman 3. So Roman 3 says, a gas of density rho with molecules moving at mean square speed c squared bar is contained in a tube of 1 meter. So this was an error, it should be L. So change it to and make it L, side L. Show that the pressure exerted by the gas is P equal to 1/3 rho c squared bar. So shall consider gas with n molecules moving randomly in a tube of length L with velocity components u, v, w in the x, y, z directions respectively, as shown below. So we shall only draw this illustration for you to know what we are doing, but this diagram carries no mark, so there's no need to draw it if you want. But for the sake of explaining, let's draw the diagram. So that is a tube. Next we shall locate a molecule, only one molecule having velocity components in all directions, in the x-axis, y-axis, and the z-axis. Then we have two surfaces of interest, because this molecule, we are going to consider this molecule moving from this side to this surface, and then collides with this surface and goes back to the surface. That is why they are shaded. So shall come and say that assuming that a molecule moves in the positive x direction with a velocity u1, as we saw in the diagram, from surface A to collide with surface B of the tube and then back to A, it implies that the change in momentum at B is equal to mu1 minus negative mu1. Why? Because after collision there will be a change in direction, but the velocity will be uniform, so it will remain u1. Therefore change in direction is denoted by a change in sign. Therefore this and this gives you 2m1, 2mu1. So that is change in momentum. Then time spent between collisions is 2lu1. Why? Because to move from A to B, that is L, and from B to A, that is another L, therefore it will be 2L. And the velocity is uniform, so it will be u1. Then the force exerted on B will be force equal to this change in momentum over, remember we said force is equal to rate of change in momentum, so change in momentum is this and the time is that, therefore the force exerted will be that. Now that was for a single molecule. Now for n molecules, the total force exerted is given by that. So these are all the molecules, u1 for molecule 1, u2 for molecule 2, and up to un for molecule n. So we are only substituting here. This was for one molecule, but now this is for n molecules. So before going to the next slide, half a mark for this, half a mark for this, half a mark for this, half a mark for that. So the mean square speed u squared bar of all the velocities in the x direction is given by that. All the velocities, all the square velocities divided by the number of molecules, which is capital N. So when I cross multiply, I'll come up with nu squared bar equal to this. Therefore, from this equation, if you remember, from here we already saw that F is equal to m over L u1 squared plus u2 squared up to un squared. So what I'm going to do, I'm going to replace this with n u squared bar. So that gives me F equal to m n u squared bar over L. Then I'll say that total pressure exerted on wall B is given by, now this was for only one direction. The total pressure for only one direction will be m n u squared bar over L. Remember, pressure is equal to force over area. So this is force divided by the area. Remember, it was a tube, so the area will be L squared. Then when I simplify, I'll come up with this. So nm over L cubed multiplied by u squared bar. So from there I realize that this nm is the total mass and this L cubed is the volume. Therefore, mass over volume is density. That means that this density rho will be equal to nm over L cubed. So when I substitute, I'll bring the whole of this bracket and replace it with density, which is rho, to come up with P equal to rho u squared bar. So before we go to the next slide, let's see marks for this slide. Half a mark for this, half a mark for this, half a mark for this pressure, half a mark for this. So taking C to be the resultant velocity of all the three components of velocity u, v, and w, it implies that c squared bar is equal to u squared bar for the x component, v squared bar for the y component, and w squared bar for the z component. But since motion of the electrons is random, it implies that this velocity is equal to this velocity and is equal to that velocity. What does that mean? It means that from this expression we shall come up with c squared bar equal to 3u squared. Therefore, when I make u squared bar, the subject will be a third c squared bar. Then from there, I'll come and remember that I had already got an expression here of p equal to rho u squared bar. So I'm going to replace this u squared bar with that expression having c. And that will give me that expression which they want. So now we shall go to part D. Part D, Roman 1 says, distinguish between molar heat capacity at constant volume and molar heat capacity at constant pressure. So here we shall come and say that molar heat capacity at constant volume is the quantity of heat required to raise the temperature of 1 mole of a gas by 1 degree Celsius. So you can either say 1 degree Celsius or you can say 1 Kelvin at constant volume. While molar heat capacity at constant pressure is the quantity of heat required to raise the temperature of 1 mole of a gas by 1 degree Celsius or 1 Kelvin at constant pressure. So that's what they wanted. Let's see marks for this slide. So half a mark for this Pythagoras theory, half a mark for this, half a mark for this, and half a mark for that, which gives you the 6 marks. Then here 1 mark for molar heat capacity at constant volume and another mark for molar heat capacity at constant pressure. So now we shall go to part D, Roman 2. So Roman 2 says, derive an expression relating molar heat capacity at constant volume Cv and molar heat capacity at constant pressure Cp. So you come and say that consider 1 mole of a gas warmed through 1 Kelvin at constant volume. The heat required is given by that. So 1 mole, then we shall substitute in the formula for heat required, which is that, then internal energy, and work done, which is pressure times change in volume. But the good here, we know that change in volume is 0, and we know that it is only 1 mole. I know that change in temperature is 1. So what we're going to do, we are going to substitute to come up with that, where n you substitute it with 1, this with 1, this with 0. So in the end we shall come up with Cv being equal to the internal energy. Then Roman 3 we shall say that, sorry, this is not Roman 2, so this was not supposed to be there. It's still a continuation of this Roman. So consider 1 mole, which is 1 mole of a gas warmed through 1 Kelvin at constant pressure. So this was constant volume, now it is constant pressure. The heat required is given by that formula, heat equal to internal energy plus work done. Therefore I'll substitute this with that, this is its still internal energy, and this is that. So next is to remember that n is 1, then delta change in temperature is 1, then also Cv, internal energy, is Cv. So I come and write that. So internal energy is Cv, n is 1, change in temperature is 1, then change in volume will be V1 minus V2, where V1 and V2 are the initial and final volumes of the gas. So when I simplify this, I'll come up with that expression. Then from there, remember that from gas laws, PV1 is equal to RT1 and PV2 is equal to RT2. Therefore, I'll come and substitute for PV2 and PV1. Then in this case, R is common, so I'll pull it out, remain with this, and this one is change in temperature, but we saw that change in temperature is equal to 1. Therefore, I come and substitute for this with 1 to come up with that expression, and when I rearrange it will be that. So basically that is what they wanted. So half a mark for this substitution, half a mark for the equation 1, half a mark for this, and half a mark for this, 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 half a mark for that. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be for solutions of physics paper 2, which I also left in some days back. So if you haven't yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video on solutions for physics paper 2 has been uploaded. And also, if you know of any student who is not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that we can all benefit as a family.